Shipra.
A very good morning to one and all. A very warm welcome to you all for the technical session 1, day 1 of the International Symposium on Synthesis and Characterization of Smart Material and their Potential Applications. The distinguished speakers for the day are Professor R.S. Katiyar, University of Puerto Rico, San Juan, USA, Professor Takayuki Ichikawa, Hiroshima University, Japan, Professor Ramphal Sharma, Hanyang University, South Korea. It's a pleasure to have you all among us. On behalf of University School of Basic and Applied Sciences, I thank you for accepting our invitation and sparing your precious time for us. We look forward to hearing your talks. The session chairperson today is Professor Shruti, Vaishali Singh, GGSIP University. Professor Singh is a recipient of National Scholarship in the year 1990, a GATE and NET qualified scholar. She did her PhD in the area of chemical kinetics from Delhi University and joined Guru Gobind Singh Indraprastha University in the year 2001 as lecturer in chemistry. She is passionate about teaching and was adjudged the best teacher at GGSIPU in the year 2003. Her research focus gradually developed in the area of nanoscience and technology. She was an active member of the USBAS core team responsible for getting financial aid of over 3 crores from DST under the aegis of Nano Mission Program for starting a postgraduate program in nanoscience and technology at GGSIP in the year 2008. Since the inception of this program, she has been closely coordinating this program. She set up her first nanoscience research lab at old Kashmiri Gate campus of the GGSIP in 2005 and initiated work on soft root synthesis of various nanostructures, including calcium phosphate, silica, polymer, nanocomposites, and ferrites. Currently, her research group is actively studying mesoporous silica and its varied forms, doped, functionalized, and even as hard templates to yield potential material for effective humidity and gas sensing applications. I request Professor Vaishali Singh to please conduct the session. Professor Vaishali.
Thank you, Shipra. Am I audible?
Yes, you are.
Thank you. A very good morning to everyone present today. The world is facing one of its greatest challenges in the form of COVID-19. These indeed are difficult and tough times. But whenever humanity and its survival are threatened, it is the spirit of mankind that emerges victorious through its many worries. So, I would like to take a moment to express our gratitude to all the COVID warriors and pray for the well-being of everyone. It is a matter of privilege and honor for me to invite Professor R.S. Katiyar to deliver the first talk of the first technical session in this symposia on synthesis and characterization of smart materials and their potential applications. Professor R.S. Katiyar did his PhD from physics from Indian Institute of Science, Bangalore, and postdoctorate from the University of Edinburgh in the area of Raman spectroscopy of ferroelectrics. He initially moved to United States as an assistant professor of physics at University of Southern California and is presently the professor of physics at the University of Puerto Rico, San Juan. There, he has been leading the Advanced Material Research Laboratory for investigations in the area of nanostructured materials and thin films for energy, memory, and sensor applications. Professor Katiyar's expertise include ceramic processing and growth of oxide films by various PVD techniques. His large number of excellent publications, over 1,200 in scientific journals of international repute, and over 24,000 citations speak about his remarkable scientific accomplishments. Professor Katiyar is a fellow of American Physical Society, Materials Research Society, Electrochemical Society, and also American Ceramic Society for his notable contributions in the area of ferroelectrics and multiferroids. Professor Katiyar has supervised 36 PhD students and 7 are currently working under him. He has been closely involved with organization of many conferences and has delivered invited talks and keynote addresses at a large number of prestigious international conferences. Without taking any further time, I now invite Professor R.S. Katiyar to deliver his talk on designing of novel room temperature single-phase multiferroics for multifunctional applications. Professor Katiyar, please.
For giving a nice introduction about me. Let me move ahead for the presentation, but can I see the presentation now? I don't have presentation in front of me. That's what I was trying to say. Share content. Where do I see?
So normally files.
Yeah. Can we see the content now? File. Okay, I can open it again. Let me see. Here. What happened?
So you can share your content.
Share content. That's what I was doing, Share content. Yes. And then
your file.
Here, this is the one, I guess. Is this last? Got it. Is that the one? Great.
Yes,
okay.
Move to full screen. Slideshow.
Okay, great. Okay. Let me remove this one. I can't remove this thing. Okay, great. Yeah, so my talk is about, let me put it full screen.
Yes, a slideshow view.
Yeah, I did that. So let me remove myself here, one corner. Okay. Is everything
oh yes, perfect.
Yeah. Is presentation visible now to everybody?
Yes, sir. Perfectly visible.
Okay, great. So now let me start with my presentation, and I would like to acknowledge the other contributors in this presentation, which are James Scott, Ashok Kumar, Ashok Kumar is at Delhi in NPL these days. Danilo Barrio Nuevo, Nora Ortega, Dilson Sanchez, and yes, Kumari, so Shalini Kumari. Let me go back. I don't see the signs going back and forth, I am already going quite ahead, actually. So is it possible I can go back? How can I go back, actually? That's...
So, by using the left arrow button, you can just normal slideshow view.
On the computer?
Yes, sir, on computer.
No, the computer is not moving. No, it's moving ahead only.
Previous.
It's just moving in one direction. In the morning, I saw that everything was there.
Yes, sir. So you can left click, and there was an option of end show, and you can restart the show.
Okay, there is left click, and then there is an app where I can see that. No, I don't see anywhere it says. And here in the bottom there is something.
Try the right.
Yeah, I got it. I got something. Something I saw in the bottom. Actually, it is written. Yeah, we are going back now. Okay. All right. So
Yeah.
yeah, I found where they are actually. The location has moved. So actually, so there are various contributors to this presentation. Most of them are actually, which are written in the first two lines, are my students and Professor Scott. Uh, and then you have Dr. Srinivasan, who is professor at Oakland University, and then Marty Gregg, who is in Queen University of Belfast. I would like to mention a few words about Professor James Scott. He is my collaborator for past 50, almost 50 years. We started our collaboration University of Edinburgh. Together we worked as in both of us as senior research fellows. And after that we moved in different places. But our collaboration continued. Unfortunately, this year on April 6th, actually, he expired in Oxford, SRE in Cambridge. So I dedicate this presentation to Professor James Scott. Okay, coming to my talk, actually, this is about my lab. Actually, I was told that I should give some description about the lab. So this is actually basically schematics of the lab. What are kind of activities that are being pursued? We are doing various applications, multiferroic. You can see most of them require ferroelectric or multiferroic materials for many of these applications. And so whether high-K materials for MOSFET or tunnel junctions for spintronic applications or photovoltaic devices. There also we utilized ferroelectric materials, lithium, and then other resistive switching memories that have got various kinds of oxide materials, the MEM capacitors, which has got basically ferroelectric materials that we have been studying, and high energy density capacitors, that's also ferroelectric materials. Then the talk that we'll be giving will be about magnetoelectric multiferroics, which is the another application actually that we will target about logic and memory devices. Other work that we have been pursuing in this lab actually were the uh, energy storage, that is basically by lithium ion and lithium sulfur batteries. Actually. And most of the details you can see in the website of speclab.upr.edu. And if you need more information, you can always send me an email and I will always supply it. Okay, multiferroics are these materials they possess more than one ferroic forms of ordering in the same phase. That is ferroelectricity, ferromagnetism, and our ferroelasticity. The magnetoelectric multiferroics show coupling between the magnetic and electrical order parameters. In other words, actually, you can switch the polarization by magnetic field and magnetization by suitable electric field. And as a result, you can have a four-fold memory actually, and also you can miniaturize the devices, which will be given in the next one here. So these are actually multiferroic materials. They have lots of device potential because they can perform multiple tasks at low power, faster speed, and lead towards the device miniaturization. So multi-state memory devices, that means you write ferroelectrically and read magneto-optically. Electric field controlled ferromagnetic resonance devices, and that can be used, and also it can be used magnetic data storage. Magnetic field induced changes in electric polarization. So that means you can use for magnetic sensors as well, and it's very, very sensitive. You can go up to 10 power minus 17, kilogauss or so, something like that. You can even read that. Actuators and transducers, that means magnetic electric control gives an additional degree of freedom to them. Actually. Dual tunability for microwave devices, which we are working these days, resulting in very efficient power transfer, actually. Multiferroic tunnel junctions that we have recently fabricated for spintronics applications. So, but what are the problems and challenges? Well, only a few single-phase multiferroic materials exist in nature. There is a weak coupling between the electric field and magnetic order parameters. So if the coupling is weak, then no matter, then applying the magnetic field will not necessarily result into the changes in the polarization. And even if it occurs, you have to apply a lot of magnetic field. So our work actually for past several years has been to design new room temperature multifluidic materials with a strong magnetoelectric coupling. Okay, for designing these materials, we started with the concept that the zirconate titanate, that is PZT, it makes very good solid solution because we have studied PT with PMN and all that. Actually, it makes very good solid solutions. Almost any amount of actually, PMN can be dissolved into PT, lead titanate. So using that concept, actually, we decided to apply it to some of these low temperature multifluidic materials. That is the PFW, which is a lead iron tungstate, and PFT, which is lead iron tantalate, and then PFN, which is lead iron niobate. All these materials are indeed multifluidic, but they are multifluidic at low temperatures, so they don't have practical applications actually. But so we decided to combine, each separately with the PZT, that is and make a solid solution of them to see what happens actually, whether the combined solution gives the multifluidic properties at room temperature or not. Well, in order to do that, we had to do ceramic sample preparations. And to do that, we required lead oxide, zirconium oxide, titanium oxide, iron oxide, and tantalum oxide or niobium oxide, actually. So, I mean, here I'm actually, although we have studied a number of multifluidic, those from PFW as well, but I'm reporting only the PFT and PFN. A PFN means niobium and PFT means tantalum. So these are the ones actually that I have actually, I will be reporting today. So we can combine all these oxides in different, proportions, and then we utilize high energy ball milling, something like 600 RPM, for about 20 hours in methanol, and we can make a very good actually powder out of that. We calcine the powder, then make the pellets, enter the pellets actually. So that way we were able to get good pellets of these materials, which are in ceramic form. Now, let me tell you that actually we have made all kinds of compositions, that is 0.1 to 0.9, that X is varying. So in other words, actually the entire family, we were able to prepare these ones. And in the next one, you'll see X-ray data. So in the XRD data, you will see that all these materials only show peaks of perovskite structure, and no phase mixing of any kind was observed. It became really a single phase material, even though it is just a complicated material. But considering that the B site is occupied by several ions, like it could be titanium, iron, or could be zirconium, and tantalum or niobium, that's considered this XRD spectra show that it is indeed a very good material that was obtained out of that. So we did both for the PFT as well as PFN. Actually, you can see all here, PFN and PFT. In order to check whether we really, what XRD is giving the information is true from other studies like, SEM, that within the grain size, you can see uniform distribution of each element, whether it is a potassium, whether it is a titanium or it is lead or it is zirconium or iron or oxygen. They're all actually uniformly distributed over the grain that we have selected, we have picked up and checked actually through SEM and EDOX studies actually. Similar things were done actually utilizing the scanning tunneling electron microscopy for PFT, PGT in some other labs by taking our samples, and they found that there is a uniform distribution over the area that they have studied actually, and the area they chose, of course, TEM, you cannot have a very big area. So you took 700 nanometer by 400 nanometer lamellas, and they found the uniformity in that case. We tried to study the X-ray spectra at high temperatures as well. And here is an example, actually, I'm giving for PZT-PFT. The XRD spectra showed, these triplets, actually. This one, actually, if you resolve them with slow speed, you get something like this one, actually. And here, this one, you will get like something like that. In other words, there are three peaks are there. And these three peaks are like here, this is 112, 211, and 121. And here it is 020, 002, and 200. So all three peaks are here and here. So these three peaks actually are associated because this structure in this temperature region is orthorhombic. As you heat the sample up above the temperature, then they become doublet, and that's the tetragonal. So we saw a definite proof of actually a phase transition, a structural transition in this material at certain temperature. And similar behavior was seen. This is for x equal to 0.4, and so for x equal to 0.3 also, we saw similar behavior. The triplet becomes the doublet actually, as you go at higher temperatures. And we analyzed the data further, and we found actually that the orthorhombic phase was indeed either P22 or PMM2. And tetragonal phase was P4 by M or P4MM. We analyzed the same data at high temperature in this case, in a high temperature X-ray. And we found when we go as a temperature change, then we studied the lattice constants, how they change. And you can see here there are three lattice constants, which is orthorhombic. And at certain temperature, there are only two lattice constants are left. So that is a tetragonal phase. So you can clearly see this dotted line clearly tells us that where there is a phase transition occurs actually. This is very, you see, it is another proof comes from the dielectric measurements. We did dielectric measurements in this material or at the function of temperature. And we can see there's the dielectric maximum occurring at that time. That at the same temperature as the orthorhombic to tetragonal phase, it changes. And this is another proof actually that we do have a phase transition occurring, or a structural phase transition occurring at this particular temperature, which is 475 Kelvin for x equal to 0.4, and it is 520 Kelvin for x equal to 0.3. We have given here where we have so much data and for almost every composition, but just typical data. I'm presenting only one for you to appreciate, to see that there is indeed a phase transition is existing in this material. We did Raman spectroscopy different. We chose actually deliberately the temperatures so that we can be in a orthorhombic phase, and we can be in tetragonal phase, and we can be in cubic phase. So in those temperatures, actually, we took the Raman spectra of the material. It was very complicated. It has 12 peaks actually. When we analyze them in detail, we find 12 peaks are there. And then at a higher temperature at 523, it remained to reduce to 8 peaks actually. And this is what it was expected in the case of actually a phase transition, or in the two phases, two structural phases actually. And in cubic phase, as one was this, since it is centrosymmetric material, and there is no more Raman scattering occurring in that one. So you can see there's no Raman features in that. So this also supports our theory about the phase transitions in this material. We have studied as a function of x actually how the phase transition temperature changes ferroelectric transition temperature. You can see that the maxima moves towards the lower temperature as you increase the value of x. And same thing actually in this. This is for PFN PZT, and this is your PFT PZT. Similar things happen actually, and losses are still low actually, up to 1. They are considered reasonable actually, but yes, so losses are low. But so we have changes in the phase transition temperature as the X composition changes in these materials for both PFN PZT and also PFT PZT. Here are the ferroelectric loops of the PFN PZT and also PFT PZT. So you can see that as you change the composition, this ferroelectric actually the remnant polarization, it actually changes, it decreases. 0.4 it is maximum, and at 0.1 it is lowest one actually, and similar things actually. And so here we have plotted how the remnant polarization changes as a function of concentration. You will see that perhaps it's probably the best one actually around 0.2 to 0.3. You can see 0.2 and 0.3 here is considered the best actually, because you have to consider for the two materials. One is PFT PZT, one is PFN PZT. This is PFN PZT and this is PFT. So in other words, for almost every concentration, there is a polarization, but quite reasonable actually. You can say all these are quite reasonable in that case. At least this one actually 0.3 is good for both of these materials actually. It's a reasonable value. Coming to the magnetic properties, yes, you can see that the room temperature magnetization, also the remnant magnetization exists at these loops, are the indicators of that actually. And here also for 0.2, perhaps the best magnetization was there actually in this case. So 0.2 and 0.3 we consider probably the most suitable materials for further studies. Yeah, here I have typically shown actually at 0.3 composition the magnetization of PZT-PFT. You see it's very smooth and going on. That shows actually there is no phase transition, magnetic transition anywhere occurring in this region, except actually in this region we don't know actually if there is somewhere actually another transition is there, but we haven't studied beyond that. So the interesting thing is actually that in these materials, if it were phase separated, then PFT and PFN, they have a nail temperature around Tn 180 degree. You see nothing around 180 degree here. That shows that the material PFN or PFT, they have made real solid solution with PZT, and they have lost the properties of the individual PFT or PFN. Because if the individual components were existing in our solution, we should be getting some kind of peak, around Tn, okay, in these materials. Also, if we can expect in these materials maybe the impurities like iron oxide, Fe2O3 or Fe3O4, they have a transition around 260 and 120. But looking at this curve, there's no anomaly anywhere near 260 degree or 120 degree. So we can safely say from all the studies that we are getting that our materials are indeed single phase materials. Coming to the losses actually, these leakage currents actually. So we can see that these materials have got very low leakage currents. We're talking about 10 power minus 10, 10 power minus 9, 10 power minus 8, in this region. And same thing true for PZT, PFN. So this is another very interesting. We really need high dielectric constant, low losses, and that's what it is. We had, and also low leakage current are extremely important parameters for device fabrications. So we consider that these materials are indeed very good for that. We wanted to know if there is any magnetoelectric coupling occurring in that one. So at that time, we didn't have any other tool, so we decided to look at only the ferroelectric loop and apply the magnetic field. Not very high yet. We had at that time 1.5 Tesla. And you can see that the ferroelectric loop actually remnant polarization changes. It actually, you can see that there's this change is there. We have plotted that change here. So that change actually clearly indicates that magnetic field can change the polarization. We did later on actually nanoscale, studies in this one. So in this case, what they do, they by microscopy, they have two kinds of domains, the red and the blue, and see how they change with the field. Actually. So there is a 3 kilos, it's very small field putting, and to see how the domains change. Actually. You can see that there is switch over the domains. We have plotted here all the domains actually, the one kind and then the other kind. And you can see that as the field changes from 3 kilo from positive to negative, there is a big change actually in the total domains. So all these things have proved actually that there is indeed magnetoelectric coupling present in this material. We decided all this work was done on ceramic so far, so we decided to make some thin films of these materials. One of the thin films that I'm reporting here is the PZT-PFT thin films. That is the made on the LSCO substrate. And LSCO was the bottom electrode actually for electrical measurement purpose. And LSCO is not magnetic, so it was okay actually. And the MgO was the substrate. So here are the pulse laser deposition parameters, for depositing the material. We got excellently X-ray, XRD spectra here. And you can see the films are all look like they are all oriented along 001, 002. There is a very small component of actually 011 here, which is something like 0.01% of the strongest peak actually. So there is a little bit leakage of different orientation, but predominantly I would say the films were indeed very much textured. Here are the polarization measurements. Actually, you can see excellent ferroelectric loop for x equal to 0.2 and 0.3, which is where I said earlier, actually, those were the most reasonable values actually of the polarization and magnetization. And here you can see very nice, ferroelectric loop. And here is the magnetic loops actually of this material for different concentrations. So, and the dielectric values were also very good. Here plotted 0.4. 0.4 becomes a little more relaxed. It will relax a little bit actually, because you can see that there's a shift in the maximum as a function of frequency. So this is an indication of some kind of relaxation occurring, in thin films for x equal to 0.4. But the most actually, ideal thing was it is 0.3 here. This is practically no relaxation of any kind, and you have x equal to 0.3 and good data and very nice dielectric constant, and losses were low. You can see the losses are very low. Coming to the magnetoelectric coupling in this material, this is very surprising and very nice. This work was done by Dr. Gopalan, Professor Gopalan at the Michigan, and getting coupling coefficients of something like 17.3, 17.3 or 17.4 volt per centimeter. This is quite high actually. This is normally was not expected in such materials, but we got indeed very good coupling. And so these materials are very promising, in fact, in that case. And as a function of frequency, it's even increasing further. And so that actually the PZT-PFT is very promising material, and we are indeed interested in making various kinds of devices with this material now. Mhm. So in summary, we'll say we have successfully synthesized a single phase PZT, PFN, PZT, PFT, and also I haven't shown you any data on this one, but believe me that we have gotten similar results with PFW, PZT as well. Since this has got a different kind of structure altogether, and these two have similar structures, so I worked in this presentation, I basically concentrated on these ones. But multiferroics as such, they are occurring in almost everyone. I have given to Professor Ramesh Ramamurthy this material to do some further studies in their labs, actually. And we have not gotten any data out of that. So these are our first attempt of making room temperature multiferroic materials through solid solutions. And we consider ourselves that we were really lucky we got it, actually. So the existence of multiferroism systems opens the possibility to explore new family of multiferroic materials at room temperature. And multiferroic materials, thin films had shown giant ME coupling that we have just shown it to you. We could actually make superlattices. We have made superlattices of these materials in order to study certain properties of these materials. But what I would show you now, another series of materials that we have recently started working on that, which is palladium substituted lead titanate or lead zirconate titanate ceramics, multiferroics. So see, this PT and PZT, these are only ferroelectrics. They are not multiferroic by itself. Now, we are substituting with palladium, which is non-magnetic actually. But we expect magnetism occurring into this material. This was done theoretically in recent computational density functional theory. They suggested that PD4 cations can substitute at the PV site, that is the A site. So, and if they substitute PD4 plus in the A site, then the resulting material will show magnetism in this one. DFT calculations also suggested that if PD4 replaces PB ion, that is the A site cation, then magnetic moment will be something like 1 microvolt. But if it replaces the Ti ion, that is the B site, then the magnetic moment will be only 0.1. So it will be much less compared to this one. So based on that theoretical computations, we decided to synthesize, lead, the palladium cation substitute in the A site, that is the PB site, and both of these materials. We chose, of course, all ball milling and all the process is the same, ceramic processing, but dopings we chose were 10% and 30% of the palladium into this materials. So here actually pure tetragonal phase formation of the material. The material resultant material was indeed still pure tetragonal phase, and it was the space group was 4 mm, and the tetragonality ratio was 1.047 here, and the XRD studies, the presence of weak Bragg peaks were observed actually for PD oxides, very weak actually. So rest of them actually, the material had a single phase actually. To be sure that we do have the PD4 and PD2, PD plus 4 and PD plus 2 in the material, we did XPS studies. And the XPS studies did show that yes, there were both of them. Actually, one is PD4. You can see PD plus 4, and this is PD plus 2, the spectra. And this is what we observe, and which is resultant of the two. And as a result, actually, that we could say, in fact, they calculated that the ratio of the two is 4/3. In other words, actually, there is a more, PD4 plus 4 times, and that is 3 times in the other. In this material, we did temperature dependence of the dielectric constant, and we found some kink in this region, actually, which is indicative of a, since at different, frequency, it is occurring at the same place. So this is indicative of actually a ferroelectric phase transition. That's what happening here. We also confirm this transition with the heat flow, and we can see a sharp anomaly at that particular temperature. So in other words, actually, we can clearly say that in this material we have a phase transition around 560 degrees. We did again the magnetoelectric measurements in this material. These are all ceramics so far. So in this magnetoelectric measurements did give some magnetoelectric coefficients, something like 0.4, 0.6. That's the maximum you could get it actually in the 10%. And same thing is, but we did not get. We got something 0.08, very small value. Magnetoelectric coefficient was smaller compared to what I have shown you in the earlier, the solid solution materials actually. But it did show magnetoelectric coefficient, and this kind of material in which the doping is taking place at the place of actually a site, which is very different compared to the normal multifluidic, the other ones that we have taught actually. And so there's a lot of future for these materials to be studied. Here are magnetoelectric coupling coefficient which we've done Dr. Srinivasan. And again, we got actually magnetoelectric coupling of something like up to 0.3 millivolts per centimeter Oersted. Encouraged by our ceramic data, we decided to make thin films of this material. And thin films here are lead titanate alone with PD 30%. And substrate was LSAT. And then material, we put bottom electrode as LSMO. This is by pulse laser deposition. So these are the growth conditions. And so the material actually, the thin films stabilized in the tetragonal phase, perovskite phase, of course. There were no impurity peaks indicating phase pure films were there. And the compressive strain was something like 2%. Surface morphology here, again, we checked actually, see if this material is uniformly distributed. You can clearly see all of the elements actually are very uniformly occurring over the region that we have investigated, which was something like, and the surface roughness was something like 4 nanometers. Okay. We also did piezo force microscopy of these thin films. You can see there is a good switching, something like at 12 volts actually in both cases, phase as well as amplitude. And that clearly shows that there is a polar switching in these materials existing, and that means there is ferroelectric electricity at nanoscale. We measure the dielectric values here. You can see the dielectric constant is around 2700 values. It is still rising, and unfortunately we were limited in dielectric constant to measure higher temperatures, something like 650, or somewhere we stop. Our systems do not work beyond that. So we could not easily determine exactly where it is peaking up actually. But that clearly shows that the material does have a tendency towards the ferroelectric properties. Here is a ferroelectric loop, that is the polarization. Unfortunately, it's very leaky, as you can see that it's not saturating. And that's because this material, as you can see here, the leakage current is very high in this material. So, and that leakage current can come because you have got two electrons, actually, PD4 plus, actually. You have got two additional electrons. They create two additional electrons that creates oxygen vacancies, plenty of oxygen vacancies it gives you. And as a result, actually, the leakage current in this material increases. So something has to be done to control the leakage current, and then the only ferroelectric loop will come out to be good. As for magnetic loop, that's fine. This is something what we didn't expect in this material, but theoretically, since it was shown, if it substitute in the A site, then it will have actually a magnetization. And we have been clearly observing the magnetic properties in this material. So that is beyond doubt that this material is multiferroic, except that the leakage current is very high, and as a result, the ferroelectric loop is not that great. Now, again, here the XPS studies were done on thin films as well, and the results are the similar one, actually, that we have both PD4 and PD2, at the A site, actually. Here we are showing actually the magnetic data over the temperature region, which is done actually with the lowest temperature. When we reach, actually, we put the field something like 0.8 and then remove the field. Then we just follow just the temperature path of that, the thermal evolution of the magnetization, and then take the dm by dt. You can see it is completely flat. There is nothing, no change in magnetic ordering in this material, in this region, because that shows that the magnetic phase transition is above the room temperature. Anyway, this is PZT-PD, which is another, instead of PT-PD, we have made PZT-PD. But the results are very similar. I mean, this growth in the same way, but again, you can see that there are phases are there, and film thickness we measured is around 300 nanometers. And again, here, the distribution of actually various elements is very uniform that you can see from this data, EDS data. And here is the AFM data. You can see that the surface roughness is something like 5.4 nanometer in this case. Here's the dielectric data. There's a moderate decrease in dielectric constant, and nearly constant loss, in this region. This is constant loss, and then suddenly around 10 to the power 5 frequency range, it starts going up actually. So these losses are basically due to the strain in the film, extrinsic contributions, oxygen vacancies, all kinds of things are there. Interface layers are there. So this material still has to be studied considerably in order to reach any further conclusion on this one. From the thin film case, in ceramic case, we could not get the transition temperature, but here we can see a peak occurring around 515 K. So in thin films of PZT-PD, there is a definite phase transition, that is ferroelectric transition around 515 K. Ferroelectric properties, that is the polarization, is again very loop, and the loop was very leaky actually, this material, as in the other case. That's mainly because of the oxygen vacancies, and that involves other conduction processes might be there too. And you can see here also the leakage current is very high. See that, these things. Magnetic properties are great. Actually, you can see the good magnetization, which is theoretically what they predicted is perfectly correct. Actually, it is magnetization. And and again, talking about the same thing, actually, that thermal hysteresis actually. It's a flat, there is nothing, magnetization hysteresis. And you can see when you take dm by dt, it comes out to be flat. So there is no transition at the low temperatures actually in this material. XPS data, they again exactly same kind of things. They are same story they tell. That is, there is a PD4 plus and PD2 plus occurring in this material. And the ratio was calculated to be 0.83 to 1. PD4 is something like 0.83 in this case. Well, I conclude my talk here. Just to say, this is later particularly that the lead substituted PT and PGT materials were synthesized in ceramic as well as thin film forms. Film thickness was something like that. Electron diffraction results suggest no signs of other phases. That is, we did have phase pure, but robust ferromagnetism was robust, no doubt about it. But leaky ferroelectric behavior were observed. Evidence of mixed oxidation states, that is a palladium ion, is PD4 and PD2. Both were actually clearly seen through XPS data. And also a good, that is the one that gave the magnetic ordering in this material. Otherwise, you should not be getting any magnetism in this material. Dielectric properties actually suggest that there is a transition around 5 and 15, which is ferroelectric transition, of course. And the ME coupling existed in all materials at room temperature, though it was low in this case compared to what the solid solution material of PFT PGT we got. Well, I thanks to all of you actually for paying attention to this talk. This work was supported by the Department of Energy grant and also National Science Foundation and the Department of Defense Air Force grants, actually, which is still active grant in this one. These are active grants yet. Department of Energy is completed. There are lots, many of the relevant publications and details of the facilities of the lab are given at this site actually. Although I think I've listed here also, these facilities, but it was too much to put in one page actually. But since you have the presentation, you can look at it, although you can go to the website and see it back. So thank you again for your attention to listen to this talk. And any comments, please let me know.
Yes. Any questions, Amar?
Ma'am, no, ma'am. Till now, there's no questions. I think the talk was informative and basic.
Everything was so clear in the talk that there are no questions?
Yes.
All right. All right. Thank you very much, sir, for giving us useful revelations and insight into the world of multiferroics. So you presented the humongous work which was done by your group in an extremely simplified and in a very straightforward fashion for all of us to really understand and appreciate. And I think that's the reason why we haven't invited many questions, because you presented the results, the data, everything, and you explained each and every slide so well, including the XRD patterns, the phases that you obtained, that I think everybody found it just a delight to watch and listen to what you had to tell us. So it was really interesting to learn how the constraint of weak coupling can be overcome by designing single-phase multiferroics, and that too, which are effective at room temperature, which I'm sure would have been a very challenging task. Usually, they are more effective at lower temperatures. I think you mentioned it also in the talk.
Yeah, I would just mention that our next talk actually is on interface mediated multiferroic, because that's way we can increase the coupling further. If we involve, of course, if they are strain mediated, then it's not good because that speed will be low. That will be speed of sound. But if we can make charge mediated, that's what we are working upon. To see if some of these materials can be taken to make interfaces charge mediated. so that the coupling goes up while we have still the speed of charge and not of the strain, So that is our work actually on the new proposal. That's what we are working on.
I'm sure you will achieve. You will achieve what you set your targets for,
Yeah,
sir. I'm sure.
I may also mention one more thing which is not relevant to this conference, but my labs are open for any researchers from India to come and avail the facilities and utilize them. There is no cost at all. I even buy materials for them. We cannot provide the travel or the other expenses, but we can take care of that. And all facilities are available to, as such, without any charge, any kind of thing.
That's so kind of you, sir. I'm sure many of the research students who are watching us, listening to it, I'm sure they would be very, very happy about it, and they should think about it seriously. Thank you so much, sir. And what I also saw from your presentation was a curious relationship between the structure, the orthorhombic, tetragonal, cubic, and how the properties are influenced by that. It was indeed very intriguing, interesting, and of course, everything was so interrelated. Sir, your talk has set the tone right for rest of the symposium. Yours was the first talk of the first technical session. It's been an honor, an absolute honor to have you today with us. It must have been past midnight now there at US, sir, and you still took out the pain to sit through and to talk to us. We are so grateful. Please accept our sincere thanks, a lot of gratitude and admiration, sir. Thank you so much, sir. Thanks.
Thank you.
So our next speaker for the morning session is Professor Takayuki Ichikawa from Graduate School of Advanced Science and Engineering, Hiroshima University, Japan. He obtained his PhD from Graduate School of Biosphere Science, Hiroshima University, in the field of theoretical physics. He joined the School of Integrated Arts and Sciences, Hiroshima University, as a research associate and then started research in the field of hydrogen energy. As a professor, he moved to Graduate School of Engineering, Hiroshima University, which is now renamed as Graduate School of Advanced Science and Engineering. His research focuses on solid-state hydrogen storage materials in metallic and non-metallic states, lithium-ion batteries, ammonia storage materials, and thermochemical hydrogen production. Professor Takayuki has more than 200 publications of international repute and over 4,500 citations. Professor Takayuki will talk about improvement of performance and functions of hydrogen storage materials. Professor Takayuki, we look forward to hearing you, sir.
Okay.
Welcome.
Okay, can you hear me?
Yes, we can hear you.
Okay, thank you. So thank you very much for kind introduction. So it's quite my pleasure to have some presentation here. And my name is Takayuki Ichikawa from Hiroshima University. And just I briefly introduce our activities and then it's going to our some recent research. Okay, this is my group, and currently just 2 professors and 2 associate professors, and just 1 associate professor is Uncle Jain from Jaipur, and he spent quite a long time in our group. And also we have many Indian members, and actually just this is quite international team. Okay, so and then so this is just our these activities, and just in order to realize a sustainable energy utilization society, so we focus on hydrogen storage material. This is quite there are 2 big kind of hydrogen storage material. One is alloy, and another is non-alloy. This is inorganic materials. And usually we focus on some inorganic materials, so-called amide-imide system, and also magnesium hydride, titanium hydride, and some mixture. And also we focus on hydrogen storage alloys to make high pressure by using this hydrogen storage alloys. So that is our activities in hydrogen storage materials. And also, just we focus on recently on lithium-ion batteries, but this is not the typical lithium-ion batteries. Actually, just we focus on magnesium hydride as anode material, or also other hydrides anode material, and also silicon anode is also quite interesting because it's quite a high capacity. And also, this is also one quite famous hydrogen storage materials, so lithium borohydride. This is also, it's quite good solid electrolyte for this lithium-ion batteries. And of course, this is quite typical solid-state electrolyte, lithium to S, P to S5. That is our target. And today's main talk is something like this lithium-ion batteries. But we use magnesium hydride or titanium hydride. That topics I'd like to introduce. And also, this is slightly different topic, but we focus on ammonia as a hydrogen carrier or energy carrier. And actually, this ammonia is, of course, quite well to use for the transportation because it's easy to be make some condensed state. Just about 10 bar pressure that gaseous ammonia can be liquefied. But actually, that pressure is also slightly high for normal use. So we focus on ammonia absorbing materials, some chloride or bromide or borohydride or some zeolite or something. But by using these materials, just we can control the vapor pressure of ammonia. And also we focus on the thermochemical water splitting by using quite untypical sodium compound redox cycle. And this is only we are focusing on this material, but actually only by heat and below 500 degrees C, we can somehow get hydrogen and oxygen from water by using this cycle. And also we focus on the cryogenic hydrogen properties. And actually, we notice some adsorbed state at such quite low temperature, about liquid state hydrogen. At that temperature, that hydrogen adsorbed state is quite interesting and have quite normal molecule properties, and but another is some quantum effect. So we focus on something like this cryogenic hydrogen properties. And actually, just this research ID. So it's I just introduced all of my publications. Please check this. And this is just an overview of our laboratories. So of course, because we focus on hydrogen storage alloys or hydrogen storage materials or lithium-ion batteries, so there are many glove boxes here. And actually, more than 8 glove box we have, and just we somehow realize non-export to the air condition. So that is quite important to characterize all of materials because the lithium or some hydrogen storage alloy is quite active to the air. So just some perfect control of the air condition, that is very important. So we usually treat these materials by using this glove box. And also, this is quite typical TG thermogrammetry or DTM mass spectroscopy, but those apparatus also located inside of this glove box. That is quite a typical situation in our group. And also, this is FTIR and pressure DSC. That pressure DSC also set up inside of glove box. And X-ray diffraction. But of course, we use some totally without exposure to air by using this polyimide film. That is totally non-oxidized state and non-water adsorbed state. So we can characterize quite detailed. And this is quite typical pressure composition isothermal properties measurement for hydrogen storage properties. And the gas chromatograph and the SCM EDX X and some electrochemical measurement are very important for us. And also adsorption property is also quite important. So our analytical method is widely spread, and also just XPS is also our own XPS apparatus also. We control this machine. And then ICP-AES, this is to characterize some elemental analysis. Okay, that is our group. Okay, just I'd like to start my content and just briefly start from background of my talk and then objectives and some experimental techniques. And then today I'd like to focus on our activities about lithium-ion batteries. So we focus on these very typical hydrogen storage materials, magnesium hydride, titanium hydride, and vanadium hydride. These materials are quite good actually for the anode for lithium-ion battery. So just I would like to explain some relationship between thermodynamic properties by using hydrogen storage system and also relationship between that thermodynamics and electrochemistry. I'd like to explain that. By the way, this is Japan, and Hiroshima is here, and quite nice place, and anytime welcome to Hiroshima. Okay, just start from background. So it's slightly long time ago, just one German group focused on magnesium hydride. And magnesium hydride is quite a typical material for hydrogen storage because it has quite high capacity. But unfortunately, this magnesium itself is quite difficult to treat because quite worse kinetic properties. Of course, potentially magnesium can absorb hydrogen at room temperature, but usually it's quite a high temperature necessary because kinetic reason. And usually just before our report, so many researchers focus on magnesium hydrogen absorption properties at more than 300 degrees C because it's quite worse kinetic properties. But one German group focused on this some catalyst by using oxide. And they reported that this niobium oxide acts as quite a good catalyst for magnesium. Of course, they reported this quite drastic kinetic improvement, but they didn't focus on the hydrogen absorption properties. But afterwards, we focus on this material for hydrogen absorption. And at the first time, we somehow realized the hydrogen absorption at room temperature, something like this. So usually, this is some hour scale or something, and at 300 or more temperature. But in our report, at room temperature, we succeeded in some hydrogen absorption properties within several seconds. It's quite a drastic improvement. So that is the starting point of our magnesium hydride work. And of course, this is just below, below room temperature, just -10 to -50 degrees C. Even at such quite low temperature, that magnesium can absorb hydrogen. And just we compare these non-catalyzed magnesium and catalyzed magnesium, and it has quite big difference. But anyway, we just performed this hydrogen absorption below 0 degrees C. That is also first time to report. And also titanium hydride also quite a famous hydrogen storage material, but it is quite a stable hydride, and also it shows it's quite worse kinetic properties. Usually, if we want to make a hydrogenated state, more than 400 degrees is necessary. But we recently noticed after dehydrogenation, about 580 degrees C and the vacuum condition, but immediately tried to do some hydrogenation. In this case, we first time noticed at room temperature was quite low temperature, titanium can absorb hydrogen. that is quite drastic properties. Actually, again, this is just weight gain, and also this is time. And we increase the temperature, something like this. But at room temperature, immediately weight gain was observed. So about 4% hydrogen can be absorbed in titanium. So that is quite drastic, but that immediately is quite important. So that means, so this titanium raw material itself should have quite active surface to absorb hydrogen. But if we expose to air or some even in glow box, so that titanium immediately oxide, make oxidation. So that means some stable surface were generated. Then that was that broke hydrogen absorption. So that is the reason why titanium shows it's quite worse kinetic for hydrogen absorption. But if we perform the hydrogen desorption, and then immediately try to do hydrogen absorption. In this case, titanium itself shows it's quite active phenomena to absorb hydrogen at room temperature. But unfortunately, this cannot be kept it long time because too active to keep that active state because immediately oxidized. But if we perform the ball milling by using acetone or some organic material, this is surprising result. So that is that shows it's at room temperature that hydrogen absorption can be seen. So that means, so by using some typical organic solvent and then ball milling, in this case, active surface can be generated, and then that solvent can cover the quite active surface, and then that can keep a long time such a quite active state. And recently, we noticed some graphite also. It's quite act as good some surface covering material. And then by using this graphite and ball milling, and then that hydrogen absorption properties at room temperature can be kept quite long time. So that is quite interesting result. So that is our activity to the titanium and magnesium for hydrogen storage alloys. And then this is totally different topics. And actually in 2008, one French group reported that this magnesium hydride as anode for lithium-ion batteries. And usually that graphite is quite famous for lithium-ion batteries, but that has only 370 capacity. And this is this y-axis is voltage. And then in the case for graphite, so at 0.1 voltage, so it shows about 372 milliampere hour per gram. But if we focus on this magnesium hydride, so just about 0.5 voltage, that time there are one quite clear plateau and another plateau is here. And then this first plateau is corresponding to the magnesium hydride react with lithium. And then lithium hydride was generated, and then magnesium was also generated as byproduct. So, of course, in the case for graphite, the lithium can be intercalated into graphite. But in this case, that the new hydride was generated. So we call this is conversion reaction for lithium ion batteries. And then second plateau is something like this. And they reported this magnesium react with lithium ion, and then lithium magnesium alloy was generated. That is slightly long time ago that they focus on this magnesium hydride as an anode for lithium ion batteries. And actually, this is done by some organic system, but our group focus on the all solid state. So that is the difference. But anyway, first time to show that this magnesium hydride as anode for lithium-ion battery. At that time, of course, we focused on the magnesium hydride as hydrogen storage materials, but they first time focus on this. And also at quite similar time, one Japanese group focused on this lithium borohydride. And the lithium borohydride, as I already mentioned, lithium borohydride is quite famous material in hydrogen storage field because it has quite a high hydrogen content. Usually, normal hydrogen storage alloy shows it's 1 or 2 weight percent. Just weight ratio is 1 to 100. It's quite a heavy storage material. But actually, in the case for magnesium, about 7 weight percent hydrogen capacity. But in the case for this lithium borohydride, more than 15 weight percent hydrogen capacity are realized. So many people focus on this lithium borohydride. But in 2007, this Japanese group focused on this material as solid electrolyte. And then there are one quite typical some structural transformation at about 115 degrees C. And then this is inverse temperature, and then this is ionic conductivity. And then increase the temperature. And after that structural phase transformation, this material shows it's quite nice super ionic conductivity. So they focus, or we focus on this material as a solid electrolyte for the lithium-ion battery. So that is background. It's slightly long. But anyway, we studied magnesium hydride as hydrogen storage material for these 15 years. And by using niobium oxide as a catalyst, some hydrogenation and dehydrogenation were drastically improved. And also we focus on magnesium hydride, lithium borohydride mixture or composite. And that is our target material. And as I already introduced, magnesium hydride for anode and lithium borohydride solid electrolyte. So we are interested in these materials. Okay, and lithium borohydride solid electrolyte. So that's in this presentation, I'd like to show some relationship between or among magnesium hydride and titanium hydride and vanadium hydride. These are quite typical hydrogen storage materials. And then in order to understand this reaction mechanism as the anode material for lithium-ion battery, this is my objectives of this talk. Okay, just briefly talk about this experimental technique. And of course, this hydride, just so-called MH. So this hydride focus on the anode material. Of course, these are purchased. And then this MH and lithium borohydride and just electroconducting material, some carbon black, so-called acetylene black, were mixed. And by using ball milling, we just were mixed state. And then weight ratio is 40-30-30 for this MH and lithium borohydride and acetylene black. Unfortunately, vanadium hydride is quite unstable. So if we want to keep the vanadium hydride state, that hydrogen pressure should be necessary. So it cannot be realized hydrogenated state. So just the starting material is vanadium itself. But for magnesium hydride and titanium hydride are quite stable. So just the starting material is this magnesium hydride, titanium hydride, and vanadium itself. And then something like this shape, tablets, some shape, this pressurized by using anode and also solid electrolyte and lithium metallic phase. And then finally, charge-discharge measurement were performed at more than 120 and 400 milliampere per gram. So because more than structural phase transformation, super ionic conductivity can be observed. So that's we set up 120 degrees C for measurement. Okay, this is the result. And we start from this. And then this is magnesium hydride. And try to get some conversion reaction with lithium ion. And then there are one big plateau, and this is plateau. And then second plateau is also observed. It's quite a similar result to the previous Nature paper. So somehow we realize by using all solid state. But anyway, for first report about this 2008 report, unfortunately, some capacity loss were observed for liquid state cell, but in our group, this report actually just some reversible capacity is much more higher than the initial capacity. Okay. So actually, this is some quite strange result because lithium can be inserted about 2,500 milliampere hour per gram, but some de-inserted or de-radiated amount is more than 2,500 milliampere per gram. So that is quite a strange result. So we focus on the mechanism of this. And actually, just as a comparison, this graphite state is quite a small capacity. But anyway, if we focus on magnesium hydride, big capacity can be observed. And of course, this excess capacity for charging process is quite wondering result. So just we focus on this. And then we just break the battery cell and each point, 1, 2, 3, 4, 5 cell, and then check the X-ray diffraction. And what is existing, we just checked everything. So of course, at this part, so magnesium and lithium hydride was observed, and then at that point, lithium magnesium alloy should be observed. And also in the de-lithiation process, so we somehow observed the magnesium hydride again, but at that time, at the higher voltage, so it's quite a strange result were observed. So that is magnesium boron hydride was observed. So actually this some side reaction was proceeding at this at this higher voltage. But anyway, we somehow characterized this material. And then finally, we just limited some charge discharging voltage, some good cycle properties were observed. And those results were reported in these papers. And then the next topic is the titanium hydride. And the titanium hydride is quite a simple reaction. But anyway, we observed it's 0.2 voltage or 0.3 voltage, one clear plateau existing. And successfully observed using lithium borohydride solid electrolyte. This is also reported here. Cycle property is slightly worse, but somehow we observed this anode property. And the final topic is vanadium hydride. And of course, as I mentioned already, vanadium hydride is quite difficult to be kept without hydrogen atmosphere. So we just started from vanadium itself. And but of course, vanadium and lithium hydride state is lithiated state. So we just started from this mixture, and quite a similar method of we just assemble the battery cell. And this is some charge discharging properties. And of course, in this case, it's lithium including state was initial. So we just start from here and then increase voltage here. So unfortunately, we observed quite clear plateau here. And then just some cycle properties are there. And the first cycle is this black line, but in second or third, fifth, up to fifth, something like this properties are observed. So, and then, so at this part, it's usually reshaped state is something like this. So actually, that voltage started from 0, but initial voltage is 0.5. So that is we observed some due to the vanadium 2H was generated. That was observed by X-ray diffraction. And also, so that vanadium hydride was generated during a mixed procedure. Vanadium and lithium hydride were synthesized by using ball milling. In this case, this hydrogen should be reacted with lithium vanadium, and then generated this vanadium 2H. And the remaining lithium also reacted with acetylene black as some carbon material for electroconductor. Then some quite high capacity was observed because this theoretical capacity is about 1,000, but this shows more than 1,000, even lose some 25% capacity loss due to this vanadium 2 hydrogen. Okay, but actually this much larger capacity can be explained by using this lithium carbon compound. And some plateau and slope corresponding to the target reaction and dissociation from lithium carbon compound respectively. So somehow we can understand this reaction by some clarified the all this investigation. Okay, and then this after second cycle, it's quite a similar profile observed. So actually, we assumed this is due to carbon materials. And for charging process, that capacity of target reaction should be decreased with increasing cycle number. And some overcapacity can be explained by the lithium carbon compound generation and dissociation. So this some slope phenomena is due to the some carbon black. And then other plateau phenomena is due to the some vanadium charge discharging properties. So we just assume something like this profile. This is voltage, and also this is capacity. We assume some hard carbon profile, something like this, and then subtract from these profiles. So in this case, somehow we can get a quite a clear result corresponding to the vanadium charge discharging properties. Okay, and then this is the lithiation process. And the first profile should be due to this vanadium to vanadium 2 hydrogen. And then second lower one is here, and the higher one is this red reaction. Okay, this plateau is corresponding to vanadium 2 hydrogen to lithium. This reaction, vanadium 2 hydrogen and lithium hydrogen. And the second plateau is corresponding to this. And somehow we can clarify it. And then this detailed was reported in this literature. Okay, so finally, I'd like to summarize my talk. So actually, as a hydrogen storage material researcher, so we, of course, every time focus on these thermodynamic properties. So that means delta H value, some reaction entropy value or reaction enthalpy value. But somehow we can obtain these entropy value, enthalpy value. So from this Nelson equation, somehow we can expect some electrochemical properties. Of course, so our focus is just lithium ion battery, and also another focus is hydrogen storage material. That relationship is quite clear by using this Nelson equation. But if quite difficult to be observed by using electrochemical technique, so in this case, we can use hydrogen storage properties investigation. And then from these hydrogen storage properties, we can somehow understand the electrochemical properties. Also, other direction is also quite interesting. So somehow we can confirm this relationship between thermodynamic properties and electrochemical properties by using hydrogen storage materials. Okay, quite good agreement observed. And that is summarized. And actually, just we focus on this quite a typical hydrogen storage material for anode of lithium-ion batteries. And some good agreement were confirmed. And of course, each result shows some strange properties. For the case for magnesium, unexpected magnesium borohydride was generated. And also in the case for vanadium, that is cycle properties are observed, but actually in this case, some carbon contribution is quite large for this electrochemical properties. And this excess capacities corresponding to vanadium hydride can be explained by taking account of this carbon as electroconductor supporting material. But actually, this electroconducting supporting material itself shows it's not such quite a good result for charge discharge properties. So actually, some synergy effects are expected. Now we are interested in this phenomena. Okay, thank you very much for your kind attention. Thank you very much.
Okay, can we have some questions? Are there any questions?
Yes, ma'am.
Okay.
Yeah, Anita Sharma. Anita Sharma, are you there?
I think questions can be written down in the chat box, and we can ask those questions, because many a times it happens that when we come to actually ask the person, then the person is not audible. This has happened earlier also. Why don't you write and type your questions in the question answer box?
Yes, my question is, have you tested this material for storage of hydrogen gas?
Sorry?
Have you tested this material for storage of hydrogen gas?
Have you tested the material for storage of hydrogen gas?
Yes, ma'am.
Which material?
The material the professor was talking about.
Which material professor was talking about? He talked about couple of materials for hydrogen storage.
Yes, ma'am.
Okay, fine. Let us ask this question to Professor Takayuki. Maybe let us see what he has to say.
So you mean hydrogen storage properties? You have.
Sir, I think the attendee is about this only.
Okay, of course, magnesium hydride, titanium hydride, and vanadium hydride, they are quite famous materials. So of course, we focus on the hydrogen storage properties, and that properties are quite well known. Okay. So, and actually, just we focus on some relationship between lithium-ion battery and, of course, that as lithium-ion batteries. So it's quite interesting material because it has quite a large, high capacity compared with graphite or other materials. But anyway, our focus is just relationship between hydrogen storage properties and electrochemical properties. And somehow we can clarify that good relationship between those properties.
And a question is from Professor Datta, sir. He's asking it, what can be the replacement of lithium?
What kind of what?
What can be replacement of lithium?
Cannot say.
Can you replace lithium with any other material, with any other ion? Okay. Lithium. Can lithium be replaced by any other ion?
Okay. Now we are trying to do some sodium or magnesium, but actually we need to find some good solid state electrolyte. Of course, due to that material, but somehow we try to get some magnesium ion conductor and also sodium ion conductor. Somehow try to get some good relationship, but now under investigation.
We have another question from Shaprajan. He's asking that does formation of magnesium borohydride hinder the lithium-ion battery performance?
Okay, actually, just a generation of magnesium borohydride. We also focus on that material as something like cathode material. But currently, it's not so good cycle properties. So actually, just a one-way reaction is just finished. So try to get some good condition to realize good cycle properties. That is current situation.
And there's a question from one of the participant, Lomas Rishi, that do you synthesize magnesium hydride, or you use them as master alloys?
That's difficult to catch.
Yeah, do you synthesize magnesium hydride, or you use them as master alloys?
Okay, just magnesium hydride. We usually obtained from commercially obtained that,
Okay.
and quite typical some chemicals.
Okay. That's all from the question answers.
Thank you so much, Professor Takayuki, for a very informative talk and for very nicely and convincingly answering all the queries. And greener fuels and sustainable sources of energy are the need of the hour. And although hydrogen, I think, is a very promising candidate for energy production, but being highly explosive, it is very difficult to transport. And therefore, your research work gains immense significance when you work upon the hydrogen storage material. And in addition to that, working upon the catalyst, which can facilitate the absorption and desorption of hydrogen. Only then can it be actually, brought to any practical use, any practical purpose. So I think it's a highly contemporary work which you are carrying out, and it holds great promises to bring about a breakthrough in the area of energy. I'm confident that all those who are attending this talk must have benefited and learned from your work. In fact, the contribution of carbon you were mentioning in the anode, which is made of lithium carbide compound, that particularly drew my interest. And the previous highlight of your work was correlation between thermodynamics and the voltage obtained, basically thermodynamics and electrochemistry, which was really very intriguing, nice, interesting, and very useful actually for practical purposes. Thank you so much. We are indebted to you, obliged that you could take out time and share the platform today and talk to all of us. Thank you once again, sir. Thank you. So now I invite the next speaker, Professor Ramphal Sharma. Professor Ramphal Sharma did his PhD from University of Rajasthan and postdoctorate from CNR Institute, Lamel, Bologna, Italy. He is at present working as brain pool professor at Hanyang University, South Korea. Prior to that, Professor Sharma was the head of the Department of Physics and Department of Nanotechnology at Dr. BAM University, Aurangabad. He is also visiting scientist at Nanotechnology Institute, Berlin, Germany. With research experience of over 30 years in the field of thin films, semiconductors, conducting polymers, nanocomposites, nanostructured metal oxides, bulk and nanostructured thin films for solar cells, with 25 PhDs and 42 MPhil students, he has about 250 publications, 2,900 citations, and an H index of 28. He holds the distinction of being on the editorial board of many reputed journals. Professor Sharma has successfully completed 19 national and international projects, and 2 more projects related to swift heavy ion irradiation are still ongoing with him. Professor Sharma has also authored a book on fundamentals of atomic and molecular spectroscopy. Today, we have the opportunity to hear Professor Ramphal Sharma on the topic two-dimensional nanostructured materials for electrochemical energy storage. Professor Ramphal Sharma, please. Can we connect to Professor Ramphal Sharma? Okay, these technical glitch are always a part of such conferences. That's okay.
attendee. सर आप पैनलिस्ट शो नहीं कर रहे हैं सर पैनलिस्ट में आप नहीं शो कर रहे हैं अटेंडी by which name? What?
Amar, can you explain what's wrong?
So, ma'am, Professor Ramphal, sir, there is some technical issue.
We are having a technical issue with him, connecting with him.
Yeah, just wait 1 or 2 minutes.
All right.
Professor Ramphal or what?
Okay.
Yes, sir.
Rajesh, I didn't see Professor Ramphal Sharma earlier also in earlier lectures. Was he there? Was Professor Sharma attending the earlier sessions?
I think so.
I think it's him. I think it's him. Okay, sir.
Just
So your video is not available.
actually.
Yes, sir. So this video is not on.
Yeah.
Now it is. Yes, we can see you, and I think we can hear you as well. No, we can't hear you.
Audible?
Yeah, now you're audible.
Can you try and drop your headphones also? Sometimes headphones also create problem.
I don't know.
Now, yeah, it's better now.
Now you
Now
hear
you are
me?
audible. You're audible. Yes, you're okay. It's okay.
Now my lecture is just opening.
Okay.
Few seconds. Now is open.
Yeah. Yes, it is. It's all there.
Now you are okay.
Yes, sir. We can see your slide.
Slide.
Yes. Perfect. Start.
Now I can start.
Please go ahead.
Okay, so thank you very much to Dr. Rajesh, and Rajesh has given me the best opportunity for the research work to present in front of you. Rajesh is working very nicely in this field, and I hope we will be continue on this same field. And the 2D materials
2D nanostructure materials. Hello? Hello? Are you hearing?
Yes, you are audible.
So
Ramphal.
2D nanostructure material for electrochemical energy storage. And the first we have to understand to sustain elevated development of nanostructure material and thin film and other materials. My voice is not clear. How to project the things? I don't know. So 2D is nanostructure materials for electro chemical storage. We have to use two types of material, polyselenia and sulfur selenium. And before that, we have to understand what is the battery actually. So battery is a chemical device store chemical energy in form of chemical means of electrochemical reaction. It converts the stored chemical energy and direct current electric energy. The electrochemical reaction in a battery involves transfer of electron from one material to another material called the electrodes through an electric circuit. So what is the meaning of cell and battery? So we have to understand the electrochemical unit responsible to call the cell. The cell is just maintain the fundamental units of the battery. So battery have different applications, portable electronic batteries, and entertainment household. We have categorized the different type of batteries, electrochemical batteries, and we have a primary batteries, secondary battery, and fuel cells. And we are working in a secondary battery, and here nickel, cadmium, nickel, metal hydride are having the big problem of memory storage, and generally the good material are lithium ion batteries. So lithium ion batteries, we are interested to making the structure. So positive electrode and negative electrodes are choosing the different materials. In between them, electrolytes we have to use through the separators. So we have to increasing the charging and the discharging capacity of the material. So from positive electrode to the negative electrode, this is called the charging process. And the discharging process is going on from negative electrode to positive electrode. So how to control the charging and discharging period and cyclic life of these ions. So we have to use different materials. For the cathode material and anode material. So my voice is not clear. So we are using the 2D nanomaterials or mainly concentrated to transmission metal dichalcogene and graphene. So we have to concentrate only two materials to understanding the physical, theoretical phenomena and structural phenomena. So 2D dimensional metal dichalcogene having a four type of materials we are interested. So one we have to concentrate to MOS2, MOSE2. And with respect to that, the application, so high mobility of the charge carriers and high specific surface area, tunable energy gap, and strongly bond excitators, and direct to indirect band gap crossover. So using these two-dimensional transmission metal dichalcogene material, and these are the smart materials. With this material, we are using the graphene two-dimensional structure, and this two-dimensional structure having the property, the graphene have a high theoretical specific surface area, superior carrier mobility, high electrical conductivity, high thermal conductivity. So on the basis, we have to consider the molysulfide and molyselenide combining with the periodic table of MO with SC2 and MOS-SC2. So before the experiment are the things, we have to make the strategy to make the battery. So two-dimensional materials having already reported for lithium-ion battery, lithium sulfide battery, selenide battery as a cathode material, and anode material is lithium metal. So we are here using of this 2D transition metal dichalcogene materials, and these chalcogene materials. So these materials are making the batteries having lithium ion air batteries, lithium sulfur batteries. So lithium sulfur batteries having a more application due to the gravimetric energy density, and we have to lithium sulfide battery we have to develop. And what the lithium sulfide battery have the problem, the insulating sulfur settling effect and volume expansion of the battery, and the application of sulfur batteries, high theoretical capacity, low cost, abundant, non-toxic sulfur battery. So we have to synthesize MOSSC2 multi-layer graphene composite for lithium sulfur battery, and with the theoretical and experimental verifications. So the theoretical verification with the sulfur batteries, theoretical is specific capacity having lower and volume capacity is higher with respect to lithium sulfur batteries, and the conductivity of the lithium selenium battery have larger than the lithium sulfur batteries. So we are using the more selenium batteries, and we have to develop first the structure, how to make the MOSS2 with the graphene. So the graphene is just inserted in the graphene layer in between the MOSS2 structure, and by first lithiation, it converts to the lithium sulfide MO, and then lithium sulfide, and we will get the reversible lithiation and the lithiation process, and by that we can develop the internal structure using the density functional theory, and we have developed the band gap of the material to transfer the electrons from the cathode of the material. So this band gap is very stable to using the more stable lithium cell selenium batteries. So in this connection, by the theoretically, we find that the MOS is to convert into the lithium sulfide, and we make the first lot of techniques are used for synthesis technique, high temperature techniques, and chemical vapor deposition technique. For the stable MOS2 is not reported in these techniques. So first, I think in the literature, the selenium acetamide preparation technique we have to develop in our laboratory, and we have developed the selenium acetamide material, and this is a very stable material, and after this we have to make the polyvinyl PPV material, and this PPV is converted into the graphene. So in this present work, you can see how to make molyselenide with the PPV annealing process, and we will get the graphene molysulfide as a active material for the cathode. So in this work, we have used this material. First, we have to characterize by the EA electron analysis, EDAX technique, and same images of the material. So the PPV before the annealing, these are the composition, and after the annealing, the selenium have 55%, and the carbon is this, and nitrogen is this. The topography is a beautiful for the active material. So in this things, the XRD also gave us the result. The PPV convert into the graphene molyselenium. So in this connection, we use the XPS survey of high resolution MO 3D and SE, and this is a full list graph of PPV before annealing and after annealing, and we can obtain the MO 3D and SE with respect to the structure. So this structure confirm that the MO PPV is converted to the graphene. The pi transition is also representing this graphene structure. So in this continuation, the Raman also proved that the D-band and D-band of the annealed sample, we get the graphene molybdenum selenide, and also you can see that the TAM, the MOSE2 in between, and then the graphene is there. This is a conformal structure. And after that, we confirm the MOS2 graphene is structure. We make the console of the battery using this structure. We are the electrolyte. We are using first 1 mole lithium phosphate fluoride ECDC 1:1, and by the CV characteristic we can confirm the oxidation state and reduction state, as we strategy that the MOSS2 with the first reduction state, it comes to the lithium sulfide in this peak, and selenium is this, and this should be confirmed by the next XRD. This is the MOS2 before the lithium, and with the lithium 0.01 volt, and we get the Li2Se, and after the oxidation condition, we have a selenium P. As the selenium have very good conductivity, so this CVV is represent the same CV as with carbon CV. So without carbon, we can use the graphene MOSS2 as active material for the battery. So after the lithium by the second cycle, we can see the L2SEC term and the gap of the D value of, and this is the oxidation state. We can confirm the oxidation is stated having the selenium. So both the state oxidation as well as the reduction is stated, we can confirm by the CV as well as our material received after these two cycles, and it is confirmed that the material is lithium selenium is totally received after the first cycle lithium, and this characterization we can confirm the rate capability with the specific capacity and number of cycles, and with the current and so 0.1 ampere per gram. This is the current density, and this current density, the recovery is very fast, and the coulombic efficiency is very high. So in this contrast with the material have 100 cycle having a current density 1 ampere per gram, having a very good specific capacity with the coulombic efficiencies. So this material can a very small material to make the battery for high capacity with the high cycles. But for the long stability, it is necessary to develop the material in the form of the hybrid side. So we have the hybrid material, and the hybrid material we have developed molybdenum, sulfur selenium, and this is the material where we have to use volume capacity and as well as theoretical specific capacity. So the making these two combination, and we will have the smart material. And this is a smart material, how to work. And this, you first we have to make the theoretical structure, and that theoretical structure to make the density of its states, and that the density states give us the thermodynamical stability structure. So the composition 1:3 and 1:1 and 2:1 having a very stable structure, and this stable structure theoretically we confirm by the DFT to conversion of the 1:1 sulfur selenium to the 1:3 lithium sulfur selenium. The total density of a state we have to calculate it, and this density state is give the answer about density of an energy of the battery, and this theoretical calculation to help us about the thermodynamically stable structure by calculation of DFT of dipole or calculations. So we have a where higher dipole values, and these high dipole values giving us the higher density states, and that density state having the more energy density of the battery. So in the contrast, we have developed the same battery with respect to initial ratio, and finally we have a 1:3 and 2:1 thermodynamically stable structure, and confirmed by the staticity by the same term and XRD, and by the EDOX calculations. By the EDOX calculation, we confirm the 1:3 and 2:1 about sulfur hybrid material for the smart batteries. So both this structure, we can see the topography is very useful, and with respect to the graphene multi-layers. And these graphene in multi-layers with the 2:1 and 3:1, 1:3 towards the more selenium, we can see this XRD JCPDS, and with this JCPDS, we can see the values of, and confirming that the similar is structure by the time element and mapping images. We also confirm the composition of 1:3 and 2:1, and the XP has also confirmed the speed MO on ASC 2P and 3P is structure and confirmed that this shifting of this peak of MOSSC and MOSSC 2:1 and 1:3. So these is confirmation that we have theoretically, thermodynamically hybrid two type of structure, and these structures are used for the stable batteries and high specific capacity. So in this contrast, you can see the graphene also present in this structure, and confirm that these both the structure have graphene. Also, we can confirm the structure. And by the CV voltammetry, we can also see that the oxidation reduction state, and the oxidation state, this is the pure Se2 and pure molybdenum sulfide, and this is the hybrid structures. These hybrid shifting of the peak in oxidation represent the presence of 2:1 and 1:3 sulfur selenium structure. So the rate capability is a magic result we have received with respect to the thermodynamically stable structure. So you can see that the 800 to 1200 and a recovery stage is a higher specific capacity, even in a 5 ampere per gram density. That is not damage the battery, and again the recycle started, and we have a very good result at the 1200 specific capacity. This is a very fast cathode material and very smart material for the useful for the battery. In this connection, we can measure the stability of the second composition. And this composition also have very good results with respect to 1:1. So you can see the stability with respect to both composition, and they are very stable and up to working 300 number of cycles. And so finally, the resistivity means R city charge transfer resistance, that the lower resistance with respect to the pure sulfur and selenium materials. So due to my voice, my lecture is not got good, I think so. So we have developed the layered structure successfully, and we have the long life of cycle at high applied current. The hybrid battery improve the battery performance at high specific capacity. The amount of the graphene related to the stability of lithium hybrid batteries. So I hope we have developed the smart material for the smart battery for long working period, and we acknowledge to our work to Professor Han for research support, and the Korean government for the particular financial support, and for me, the NRN granted the grant bill, and financial support will also get from the Austria, and thank you very much to all of you to listen my lecture, because my voice is not so clear. Yeah, I try my best from here. Thank you very much.
So you communicated quite well. Thank you very much. Amar, the floor is now open for questions. Do we have any?
Yes, ma'am. There's a question from Kunal. How to convert indirect band gap material into direct band gap?
Okay, so we have to make the compositions inside the material. So particular composition will convert on indirect to direct material.
Okay. So there's another question from Dr. Karthik. Which one is the best 2D material for energy storage applications among 2D graphene and 2D MXene?
2D graphene is the best, and the multi-layer.
Okay. The same question from Dr. Sudhanshu. Can you tell us about the tailoring of direct to indirect band gap? Its physical significance.
Tailoring of the direct and direct band, we can do with respect to temperature and composition.
That's all from the question answers panel.
Okay.
So actually, sorry for the communication. A lot of the disturbance with me here.
No, you communicated perfectly. I think everything was very clear in your presentation. There was no problem at all.
Okay, thank you. Thank you, madam. Thank you.
Yes. So two-dimensional nanostructures have been, in fact, one of the most studied and most favorite materials amongst most of the nano scientists and nanotechnologists who are keen on studying any sort of nanomaterials. And two-dimensional transition metal dichalcogenides particularly have gained immense importance on account of their tunable band gaps as one goes from bulk to few layered flakes, which makes them potential materials for innumerable applications. In fact, two of the questions were directed on these properties of TMDCs only. And so further, your group has developed hybrid materials using graphene and TMDC and combining them with various other materials, and also tested them for efficiency as cathode for lithium selenide battery. And not only that, you have also corroborated your results by doing theoretical calculations using DFT theory, and you have arrived at a particular stoichiometry which can give us the best results and perhaps develop that material. I think it's a very good work. A huge amount of work was shown in these slides. And sir, thank you very much, Professor Ramphal Sharma, for connecting with us today and sharing your work with us. I am sure everybody, whosoever is working in this area, and even those who are not working, would realize the amount of work that you have put in to show the results that you could show us today. Thank you, sir. Thank you again.
Okay. Thank you very much, madam. And I hope.
Thank you.
I will help you. Anybody in this materials. If they are interested, and they can come to me directly.
Very nice. Thank you so much. So kind of you, sir. Thanks.
Thank you.
And before ending this session, I would like to say something to the young students who are with us today. Science provides us answers to why and how phenomena happen the way they do. The understanding of science should be complete. Dig deeper and find the fundamental answers. With strong fundamentals, believe me, the journey to great scientific and technological feats will be truly delightful. Thank you very much for your attention, and enjoy the next 2 days of the symposia and make the best of it. Thank you.
Thank you very much, Professor Vaishali. This has been a wonderful, enriching, and informative session indeed. I thank the distinguished speakers for the day, Professor R.S. Katiyar, Professor Takayuki Ichikawa, and Professor Ramphal Sharma, for your interesting and thought-provoking talks. I'm sure the participants have thoroughly been interested and enjoyed today's session. It was very nice to go through the perspective of the latest research in the field of multiferroics, hydrogen storage, and energy storage material. Thank you for accepting our invitation and enlightening us with your views. Today's session is now drawing to its close. I thank you all for your gracious presence. We shall meet again tomorrow at 10:30 a.m. for our day 2 of the seminar. The eminent speakers for tomorrow will be Professor Ashok Moolchandani from the Department of Chemical and Environmental Engineering, University of California, USA. Professor Absar Ahmed, Director, Interdisciplinary Nanotechnology Center, Aligarh Muslim University. Professor Mahendra D. Shirsat, Department of Physics, Dr. Babar Sahab Ambedkar, Marathwada University, and Professor Neeraj Khare, Department of Physics, IIT Delhi. Thank you once again. Thank you and see you tomorrow.